This is the cover of the golden record that was sent on Voyager 1 and 2. If you look closely at the lower left corner, you can see a peculiar map. It defines the position of our sun, utilizing 14 pulsars of known directions from the sun. It is believed that any intelligent life coming into contact with the record should be able to decode this and find our position in the universe. So, what are pulsars, and what makes them such ideal markers? In 1965, Anthony Hewish, a radio astronomer at the University of Cambridge, secured funding to build a new radio telescope to study interplanetary scintillation, the twinkling of radio sources caused by the solar wind. The telescope, known as the Interplanetary Scintillation Array, consisted of 2,048 dipole antennas spread over 4.4 acres at the Mullard Radio Astronomy Observatory. Completed in July 1967, it operated at 81.5 MHz and was designed to detect rapid fluctuations in radio signals from quasars, distant galaxies with active nuclei. Hewish assigned Jocelyn Bell, a 24-year-old graduate student, to assist with the project. Bell's role involved operating the telescope, analyzing data, and identifying scintillation patterns. The telescope produced paper chart recordings, which Bell manually reviewed, a labor-intensive process requiring keen attention to detail. In August 1967, while analyzing chart recordings, Bell noticed an unusual signal, a series of regular pulses occurring every 1.337 seconds. The signal, dubbed scruff due to its messy appearance on the charts, stood out because it did not resemble the random fluctuations of scintillating quasars. Initially, Bell and Hewish considered terrestrial interference such as radio broadcasts or local electronics, but the signal's consistency and sidereal timing, that is, it was aligned with the fixed stars matching Earth's rotation relative to the celestial sphere, suggested a celestial origin. By November 1967, Bell confirmed the signal's periodicity using a high-speed recorder, revealing pulses lasting about 30 milliseconds, precise to within microseconds. The source, located in the constellation Vulpecula, was designated CP1919. The regularity of the pulses led to speculation about an artificial origin, and the team jokingly referred to the source as LGM1 for Little Green Men, reflecting the possibility of an extraterrestrial signal. To test this hypothesis, Bell and Hewish conducted follow-up observations. They calculated that the pulse's Doppler shift matched the Earth's orbital motion, confirming a cosmic source within the Milky Way. The absence of additional signals, such as modulated patterns typical of communication, argued against an artificial origin. By December 1967, Bell discovered a second pulsating source with a different period of 1.188 seconds, further suggesting a natural phenomenon. The presence of multiple sources with distinct periods made an intelligent origin unlikely, as it implied multiple civilizations broadcasting in a similar manner. Hewish consulted with colleagues, including theorist Fred Hoyle, to interpret the signals. By late 1967, the team hypothesized that the pulses originated from rapidly rotating neutron stars, whose magnetic fields accelerated charged particles to produce beamed radiation. When these beams swept across Earth, they appeared as pulses, akin to a lighthouse. The short pulse periods required rotation rates of up to several times per second, feasible only for compact objects like neutron stars due to their immense density and structural stability. The idea of neutron stars had been around for decades, rooted in the discovery of the neutron and theoretical work on stellar evolution. In 1932, James Chadwick discovered the neutron. This breakthrough prompted physicists to speculate about stars composed primarily of neutrons. In 1934, Walter Baade and Fritz Zwicky proposed that neutron stars could form in the aftermath of a supernova, the explosive death of a massive star. They suggested that a star's core, compressed to extreme densities, would collapse into a compact object where protons and electrons combined to form neutrons, stabilized by quantum degeneracy pressure. Their idea was radical, as it implied objects with densities comparable to atomic nuclei, roughly 10 to the 17th kilograms per cubic meter, equivalent to the mass of the sun squeezed into a sphere 10 to 20 kilometers across. However, their hypothesis lacked observational evidence and was largely overlooked for decades, as astronomers focused on more accessible phenomena like main sequence stars and white dwarfs. By the 1950s, advances in nuclear physics and stellar evolution revived interest in neutron stars. Theorists like Lev Landau and J. Robert Oppenheimer explored the physics of ultra-dense matter, predicting that neutron stars would be highly magnetized and rotate rapidly due to the conservation of angular momentum during collapse. In 1964, Thomas Gold and Franco Pacini independently suggested that rotating neutron stars could emit electromagnetic radiation, potentially observable as periodic signals. These ideas set the stage for the pulsar discovery, though no one had yet detected such objects. Thus, when Hewish and his team observed the regular pulses in 1967, they were able to connect them to the predicted emissions from rotating neutron stars, confirming a long-standing hypothesis. Neutron stars are extraordinarily dense, with a mass density of approximately 10 to the 17 kilograms per cubic meter, comparable to atomic nuclei. Their structure consists of a crust approximately 1 kilometer thick lattice of neutron-rich nuclei and degenerate electrons transitioning to a neutron superfluid at deeper layers. An outer core, approximately 9 kilometers layer of superfluid neutrons, superconducting protons, and electrons responsible for most of the star's mass, and an inner core, a poorly understood region possibly containing exotic matter like quark gluon plasma or hyperons at densities exceeding nuclear saturation. Neutron stars possess extreme gravitational fields, approximately 10 billion times Earth's field, and rapid rotation, inherited from the progenitor star's angular momentum. Young neutron stars rotate at periods of 1 to 100 milliseconds, slowing over time due to energy loss. Neutron stars possess extreme gravitational fields, approximately 10 billion times Earth's field, and rapid rotation, inherited from the progenitor star's angular momentum. Young neutron stars rotate at periods of 1 to 100 milliseconds, slowing over time due to energy loss. Neutron stars also have intense magnetic fields, typically 100 million to a trillion Tesla, a trillion times stronger than Earth's. These fields arise from the compression of the progenitor star's magnetic flux during collapse, amplified by dynamo processes in the convective core. In some neutron stars, known as magnetars, fields reach 10 to the 14th to 10 to the 15th Tesla. The magnetic field is generally modeled as a dipole, with its axis often misaligned with the rotation axis, a key factor in pulsar emission. The intense magnetic field acts as a generator, accelerating charged particles, electrons, positrons, or ions along the magnetic field lines toward the magnetic poles. As these particles move at relativistic speeds, they emit electromagnetic radiation, primarily via synchrotron emission, where charged particles spiraling in magnetic fields produce radiation. Relativistic effects cause this radiation to be beamed in the direction of particle motion, forming narrow cones of emission at the magnetic poles. Since the magnetic axis is typically misaligned with the rotational axis, the beams sweep across space as a neutron star rotates, similar to a lighthouse's rotating beam. This sweeping produces the characteristic pulsing effect when the beam crosses an observer's line of sight. The radiation spans multiple wavelengths, including radio waves, visible light, X-rays, and gamma rays, though radio emission is the most commonly detected. This brings us to Voyager's Pulsar Map. The Voyager program was initiated by NASA to explore the outer planets of our solar system. Voyager 2 and 1 were launched in August and September 1977, respectively, taking advantage of a rare planetary alignment that allowed efficient gravitational assists. As the spacecraft was destined to eventually leave the solar system, the inclusion of a message for potential extraterrestrial finders was proposed. The idea for the Golden Record was spearheaded by a team led by astronomer Carl Sagan, with contributions from scientists, artists, and engineers, including Frank Drake, Anne Druyan, John Lomberg, and Linda Salzman Sagan. The Pulsar Map was inspired by earlier work on the Pioneer plaques, launched in 1972 and 1973 aboard Pioneer 10 and 11. These plaques also featured a Pulsar Map designed by Drake and Sagan to indicate Earth's location. The Pulsar Map is a two-dimensional diagram with the Sun at the center, from which 14 lines radiate outward, each representing one of 14 pulsars. The key elements include a central point representing the Sun, serving as a reference point for all measurements. Radiating lines where each line corresponds to a pulsar with their length proportional to the distance from the Sun to the pulsar. Scaled for the diagram, and the angle of the line indicates the pulsar's position in the sky, though as a two-dimensional projection of three-dimensional space. Hash marks along each line form a binary number encoding the pulsar's pulse period, the time between its regular emissions. A nearby diagram shows the hydrogen atom in its two lowest energy states, with a line and digit 1 indicating the hyperfine transition period as the fundamental time unit, approximately 7.040 times 10 to the negative 10 seconds. The hyperfine transition of hydrogen is a specific transition between two energy levels within the hydrogen atom's ground state, primarily due to the interaction of the electron and proton spins. This transition emits a photon with a wavelength of 21 centimeters, making it a key characteristic of the hydrogen atom. This transition is a universal constant, as hydrogen is the most abundant element in the universe, and its hyperfine structure is detectable via the 21 centimeter line in radio astronomy. The diagram indicates that the hyperfine transition period is the fundamental time unit for interpreting all temporal data on the record, including the Pulsar Map. A 15th line points to the galactic center, providing a broader galactic context, and a uranium-238 sample with a half-life of 4.51 billion years serves as a radioactive clock to estimate the launch epoch. To decode the map, read the binary number by interpreting the hash marks as bits. Presence equals 1, absence equals 0. Convert the binary number to decimal. This value represents the pulsar's pulse period. Using the decoded pulse periods, match them to known pulsars in the galaxy. Pulsars are identifiable by their unique periods, so an extraterrestrial civilization could measure the pulse periods of pulsars in their sky. The 14 pulsars on the Voyager map include well-known ones from 1977, such as PSRB 1919 plus 21, the first discovered pulsar, and the Crab pulsar, with periods ranging from approximately 0.033 seconds to several seconds. By identifying these, the civilization can determine which stars are referenced. The length of each line on the map represents the distance from the Sun to the corresponding pulsar, proportional to the actual distance but scaled for the 2D projection. The angles between the lines provide directional information, though this is a simplified view of 3D space. With 14 points, the relative geometry should be sufficient to approximate the Sun's location. Using this, the civilization can triangulate the Sun's position relative to these pulsars, effectively locating the solar system. The selection of pulsars for the Voyager Golden Record was based on several reasons. Each pulsar's pulse period is distinct, ranging from milliseconds to seconds, making them easily recognizable and distinguishable from other celestial objects. This uniqueness is crucial for any civilization attempting to decode the map, as they can measure pulsar periods in their sky and match them to the encoded values. Pulsars' pulse periods are among the most stable natural phenomena, with changes occurring at predictable rates. This stability allows the map to serve as a temporal reference, enabling recipients to calculate how long ago Voyager was launched by comparing the encoded periods with current observations. As noted in a PBS article, Frank Drake predicted that aliens could use this change to estimate the launch epoch, leveraging pulsars as cosmic clocks. With pulsars spread across the galaxy, the map uses 14 of them to provide a network of reference points. The relative positions and distances encoded as line lengths and angles on the map allow for triangulation. Even if only a subset of the 14 pulsars is observable from a given vantage point, the pattern should be sufficient to approximate the solar system's location. Pulsars are a natural astronomical phenomenon, detectable with radio telescopes, which any advanced civilization would likely possess. Their discovery in 1967 by Jocelyn Bell Burnell and Anthony Hewish, and subsequent cataloging, suggests they are a fundamental feature of galactic structure. The map's reliance on pulsars assumes this universal familiarity, enhancing its decipherability. Given Voyager's trajectory, potentially traveling for billions of years, Pulsars' longevity ensures they remain viable reference points. With lifespans up to billions of years, pulsars outlast many other celestial markers, such as variable stars or planetary systems, making them suitable for an interstellar message. One of the most significant challenges is the map's diminishing accuracy over cosmic timescales. Pulsars, rapidly rotating neutron stars, are not static. Their positions shift due to galactic rotation, and their pulse periods gradually increase, spin down, as they lose energy through radiation and magnetic braking. Over millions or billions of years, these changes could significantly alter the map's reference points, making it difficult for a future civilization to locate Earth precisely. The map's decodability poses another major challenge, as it assumes recipients possess specific astronomical and mathematical knowledge. The map encodes the pulse periods of 14 pulsars in binary, using the hydrogen atom's hyperfine transition period as a universal time standard. However, there is no guarantee that an extraterrestrial civilization would recognize pulsars, understand binary encoding, or interpret the hydrogen diagram as intended. Advancements in pulsar research since 1977 have led to critiques that the map's data is outdated. The map was based on the best pulsar data available at the time, such as the periods of well-known pulsars like the Crab pulsar. However, subsequent discoveries and more precise measurements have expanded the pulsar catalog and refined period estimates. This suggests that the map's selection of 14 pulsars may not be optimal or comprehensive by today's standards, potentially complicating identification for a civilization with access to more recent astronomical data. The 2002 ATNF Pulsar catalog, for instance, provides far more detailed information than was available in 1977, underscoring the map's obsolescence.